Hello, Professor Bianchi and Professor Otumbina. It's my great honor to share my research topic with you. I'm Lin Meng, a PhD student from Tongji University. This presentation will be divided into three parts: the general information, recent research projects, and publication. I was born on May 30, 1999 in Shandong Province, China. My current research interests include high-speed PMSM drives, sensorless control, stability analysis of drive systems of LC filter, and data-driven motor monitoring. I excel at MATLAB, Simulink, Python, C, and LaTeX. From 2017 to 2021, I pursued my bachelor degree in vehicle engineering at Jilin University. I have received 3 times the first prize scholarships and merit student, and was honored as an outstanding graduate upon graduation. I also participated in mathematical contests in modeling and earned a meritorious award. After graduating from Jilin University, I was recommended for admission to Tongji University to pursue a PhD degree directly. The subsequent research and published papers were all completed during this stage. The first research topic I encountered during my PhD study was the key R&D program of Jiangxi Province of China, which is to develop and apply silicon carbon wide bandgap semiconductor all-in-one electric drive systems for commercial vehicles. The water-cooled high-pin motor is 12,000 RPM permanent magnetic synchronous motors with peak power up to 144 kilowatt and peak torque up to 342 Newton meter. Among the tasks assigned to Tongji University was the development of the software for motor controller. This slide shows the experimental setup and the overall control systems of this project. We also completed efficiency tests on the system and on inverter. As the student leader of the project, I was responsible for developing carrier-based overmodulation, hybrid calibration strategies, self-commissioning method, and torque estimation method. In particular, I would like to introduce the high-precision torque estimation algorithm that is suitable for low carrier ratios. The second-order generalized integrator frequency locked loop can surprise DC offset and harmonics, and there is no need for position sensor signals. Since SOGI can generate the corresponding orthogonal signals, we can use the mathematical relationship of orthogonal signals to derive the frequency, which is quite different from the traditional one. And the estimated frequency can be simply obtained as the following equation. The discretizing method use twisting method with pre-wrapping. Note that the denominators of the DZ and QZ are identical, therefore they can share the same structure with only the different coefficients of the numerators. This slide shows the experimental results. The sudden disturbance in estimation error during torque step change is caused by the sampling delay and the filtering in torque transistors. The maximum torque estimation error is 6.4 Newton meters, occurring at 4,000 RPM, which may be caused by a mismatch of the resistance parameters due to temperature rise. With the speed increasing, as shown in C and D, the torque estimation error decreases. In addition to torque estimation, the new FLL proposed in this paper can track the motor speed with a satisfactory accuracy. The main focus of my PhD research is on high-speed air compressor system for fuel cells with maximum speed up to 90 and 120 kilorevolution per minute. To reduce the PWM current ripple and alleviate PMI problems caused by high-speed switching frequency of wide bandgap semiconductor, one promising solution is to install the LC filter between a conventional voltage source inverter and the motor. However, as the order of the control system increases, more sophisticated current and sensorless control strategies are required. On one hand, to minimize the need for additional sensors and to achieve more accurate precision estimation, additional states must be estimated. For another hand, on another hand, the LC filter introduces resonant problems, which require additional active damping algorithms to suppress. Otherwise, stability issues may arise. We developed the overall control systems shown here with dedicated active damping current controller and adaptive observers. In order to achieve high accuracy control and observation, the system needs to discretize the to zero auto-hold equivalent model. First, we proposed a filter-based active damping current controller, which consists of the dynamic decoupling controller and active damping filters. The active damping filter method primarily achieves resonance suppressing by adjusting the phase frequency characteristics of the open loop transfer function. Since the open loop transfer function are cascaded, the phase of system are simply addition. According to the definition of Nyquist stability criteria, in order to stabilize these control systems, the phase frequency of the system at the positive resonant frequency must avoid traversing negative pi plus 2k pi. The solution to these inequalities represent the phase range that the filter should provide at different resonant frequency. The boundaries of the inequalities are plotted, and the stable phase regions are denoted by the blue shadowed area. Using the proposed general graphical method, we can directly compare different active damping filters and filter with parameters variation. The method allows direct visualization of how parameters changes affect the stable region. Comparative analysis also reveals that the best performance can be achieved by applying all-pass filter for inverter current feedback control. The proposed current controller is designed using all-pass filter combined with the dynamic decoupling controller, where the R of the all-pass filter and the gain K of the decoupling controller are co-designed to satisfy the system's phase margin and gain margin requirements in both low frequency region and high frequency region. When PM1 equals PM2 equals 1/3 pi, the angle can be calculated at a different cutoff frequency as a boundary of the stable region. The interaction of the high and the low frequency stability boundaries defines the maximum achievable K and corresponding R at a given speed, satisfying the system stability margins requirement while ensuring adequate dynamic performance. We also conducted the robustness analysis against single parameters, multi-parameters, and controller parameters. The parameters selection method proposed in the paper incorporates 4 frequency domain stability indices, ensuring parameter robustness across a wide range. We also conducted the comparison experiment with the state-of-the-art method. The proposed APF method has similar motor phase current PhD values and steady-state performance. Notably, the proposed method requires few computational resources and time. And the parameter robustness is also verified, which is identical to the analysis. So far, the designed current controller has been 2 degrees of freedom, only considering the resonant suppressing and decoupling control, while disturbance rejection performance has not been taken into account. Therefore, we propose a 3 degrees of freedom current controller that also achieves disturbance rejection without extra sensors and observers. The detailed structure is shown here, and the GI and the GU are employed to simultaneously configure the low-frequency motor pool and the high-frequency resonant pools, thereby strengthening the anti-disturbance capability and achieve effective resonant suppressing. And the GC is employed to achieve dynamic decoupling. The board diagram of disturbance transfer function is also depicted here. Evidently, the proposed resonance suppressing and anti-disturbance structure can effectively suppress disturbance at both low frequency and high frequency. A decrease in beta resulting in a gradual enhancement of the anti-disturbance performance of the system. To enhance parameter robustness, two additional controller parameters are designed to accommodate parameter variation. By selecting appropriate parameters, the robustness can be greatly enhanced. The robustness analysis also executed for single parameters and multi-parameters. As can be seen, the proposed method can tolerate a much larger parameter mismatch than filter-based active damping method. Because the algorithm proposed in this paper also considers the disturbance rejection performance of the controller, its current spikes are smaller than those of algorithms which do not consider disturbance rejection performance. Although the 3-degree of freedom controller has the most complex structure, it offers the best steady state and dynamic performance with proper parameter design. It can achieve extremely high parameter robustness. With respect to sensorless control, we propose a discrete time adaptive for order observer composed of for order state observer and two adaptive laws. For order state observer is designed in discrete time using direct pole placement. Furthermore, if we linearize the observer's estimation on the operating point, we can see that there are PM flux arrow component and angle arrow component in the current arrow component, and the two are orthogonal. This allows us to independently design adaptive laws for the identification of each parameters. This paper employs a simple integrator for smooth PM flux estimation and a type 3 phase-locked loop for speed estimation. It's also necessary to combine the for-order observer with adaptive laws to perform stability analysis of the entire adaptive observers. The results reveal a wide feasible range for observer parameters, validating the robustness of the analysis of the design. Finally, the effectiveness of the study sensorless algorithm is verified on a 30 kilowatt high-speed motor bench with a maximum speed of 90 kilo revolutions per minute. At low speed, the RF starting method is employed to force the motor to the lowest speed, 5,000 RPM, at which the sensorless observer can operate reliably. Not only the precision estimation error during acceleration is around 0 degree, but the estimation PM flux closely matches the nominal value of 0.026, validating the effectiveness of the adaptive laws. The following section covers motor condition monitoring based on data-driven algorithms, focusing on two aspects: motor temperature estimation and sensorless control. Let me first introduce the data-driven temperature estimation algorithm. As shown in this slide, left side are the sensor-based method. All this method requires additional extra sensors, increasing the system cost. However, for sensorless method, it can further divided into thermal sensitive parameter tracking (LPTN) and data-driven. The last two are non-invasive method and are currently the mainstream and the future trend. Unlike traditional LPTN, where the low order like accuracy and high order require numerous parameters and necessitate FEA support, we introduce lightweight neural network to directly correct losses, thermal resistance, and capacitors, thus characterizing the time-varying property of losses and thermal parameters. Neural networks can offer higher fitting accuracy, do not require complex prior knowledge, and are more general. We conducted relevant validations on a dataset of 60 kilowatt water-cooled motors. We also compared with conventional LPTN algorithms, neural network, and the state-of-the-art algorithm. The proposed method has the smallest estimate error and can well tracked the real temperature. According to and this is another profile. The next is the sensorless control. Currently, conventional model-based methods at low speed mostly use nonlinear observers, which are complex to tune and difficult to analysis. However, neural network learns the mapping from the current and voltage signals to position information. It can directly train on relevant data and reliably developed. This is the detail of the network construction. It combines the CNN and the LSTM. We also conducted a related test on a 47 kilowatt automotive motor. The proposed algorithm can achieve full load operation at 3.3% percentage of rated speed, and the electric angle error is within plus or minus 4 degrees throughout the entire test condition. During my PhD studies, I published 6 papers, including 4 journal papers, 2 of which were top-tier journals, IEEE TTE and IEEE TPL, as well as 2 conference papers. Additionally, I hold 2 granted Chinese invented patents focusing on the complex vector compensator and motor speed controller. Since this is only a brief introduction, please feel free to contact me if you have any questions about any details or any algorithm. Thank you very much for your time and consideration.